Today we will discuss chapter 26, Inference for Regression. Under that, we will discuss linear regression t-test. We only have a t-test, but it's not just t-test. The full test ID is linear regression t-test. As usual, I have posted this lecture on Canvas, so please go ahead and download that, and then you can watch the video and fill the blanks with me. To understand the materials discussed in this lecture, you will need chapters 4 and 5. In chapter 4, we discussed the scatter plot and the coefficient of correlation. In chapter 5, we discussed how to fit a simple linear regression equation. I hope you still remember those. We do regression for the relationships between two random variables, two quantitative random variables. One random variable is called the independent random variable, also called the explanatory variable, which we take onto the x-axis. And then the other one is called the dependent random variable, or more correctly, the response variable, which is taken as y. When a data set is given to you, we can draw the scatter plot. When you do the scatter plot, if the scatter plot shows a linear shape, this is an increasing scatter plot, or you can also have a decreasing scatter plot between those two random variables. In these situations, we can fit a simple linear regression equation. For this one, I can obtain a positive linear relationship. For this one, I can obtain a negative linear relationship. This is the graphical way to visualize the connection between the two random variables x and y. We also have an analytical way to quantify the strength of the linear relationship between the two random variables. That is by calculating the coefficient of correlation. We said the coefficient of correlation is given by lowercase r, and this is going to be a value between -1 and +1. If your r is close to +1, then we must have a nice increasing linear relationship. If your r is close to -1, then we must have a nice decreasing linear relationship. If your r is close to 0, that means the scatter plot will simply have some random data points everywhere. There is no identifiable linear relationship. Also, if your r is close to 0, there may be a relationship still existing between x and y, which is not linear. For example, we may have something like this. This is a parabolic relationship. Your r, which is the strength of the linear relationship, could be still very close to 0 for this case as well. So r is close to 0 does not mean that there is absolutely no relationship between the two random variables. What we can say is, if your r is close to 0, there is no linear relationship. In case, if your r is away from 0, which means if it is close to +1 or -1, or on the other hand, if your scatter plot confirms that there is a linear relationship, increasing or decreasing, then we go for the next step. The next step is to derive that equation. We have a sample of data. Of course, you will have pairs of data. You have x and corresponding y readings, and then you can input them into your calculator and obtain a nice equation, straight line, for the relationship between the two variables. We called it the least squares estimate of the regression equation. We have to keep another step forward. That's because no matter whether there's a strong linear relationship or maybe a moderate linear relationship, as we decided based on the graphs and r, once you enter the data into your calculator, it will always give you an equation. Now that equation will have the form y equals a plus bx. In those two chapters, we had a slightly different form of that equation. We wrote that equation as y equals ax plus b. But for some small reason, for inference, we do not write it as y equals ax plus b. Instead, we will write it as y equals a plus bx. Here's the reason actually. If you look at any research published on journals regarding linear regression, they always use b for the slope, estimated slope. So that's the reason we would prefer y equals a plus bx form. So let's see it real quick again for chapters 4 and 5. We wrote down that equation as y equals ax plus b. For chapter 26, you will write that equation as y equals a plus bx. So from this point on, please remember, we are going to use this equation, not that version. Of course, when you write the estimated equation, you can always write a y hat. Remember? We write a y hat. That's because I already have a data set. I have x, I have y, and using x and y data points, I can estimate this equation. Now, this equation also gives you a y value. Now, that y value is the calculated y value. You can plug in these x values in this equation and calculate a corresponding y value. And that y value will be slightly different from the observed y values. So the observed y values are written as just y, and the estimated y values using this equation can be written as y hat. So y hat can be calculated for each x value. And also we did residual analysis and so many other things as well during the chapters 4 and 5 discussions. The residuals were calculated as y minus y hat. Let's go to point number 1. We can see the reason why we actually write down the equation in chapter 26 as a plus bx rather than ax plus b when we discuss parametric equation and the estimated equation. Of course, for point number 1, this is the estimated equation. And then we need the parametric equation. Of course, these are estimated values. This is the estimated slope. This is the estimated y-intercept. What could be the true values? We will never know them, exact values. But the true values exist. Our objective is to use some sample estimates and look for the true values through hypothesis testing. When you use those true values in the equation is called the parametric equation. The parametric equation is written this way: y equals alpha plus beta x. So with the Greek letters, this equation is called the parametric equation. We do not write a hat for the parametric equation because these are the correct y values if you know the exact values of these parameters. So even if you go ahead and collect the data, those collected data will not be as accurate as the values given by this equation because these are the parametric values. So this is called the parametric equation. In a hypothesis test, what we do is we check for the significance of the slope parameter beta. We do not worry about the intercept. Intercept is very easy. You can simply go ahead and calculate the mean for the entire data set, and then if there is no slope in the equation, then the equation will look like this. In this case, you of course do not need a proper regression relationship between the two random variables. So basically, what we do is we see if beta is significant. Should it be definitely included in the equation? That's the target. If it does not have to be included in the equation, all you have to do is to take average of the y values to find A. And then we are done and we can stop there. It is not called a regression equation. To call something a regression equation, you must have beta. In fact, you must have a significant beta. Now, what do we mean by significance? That's what we are going to see under chapter 26. There's another additional comment. We said this is the parametric equation, y equals alpha plus beta x. The estimated equation was written as y hat equals a plus bx. Sometimes the estimated equation is also written this way. Y hat equals alpha hat plus beta hat x. Just to say, alpha hat is the estimated value of alpha and beta hat is the estimated value of beta. For this class, you can use any of these two equations for the estimated regression equation, but in your calculator, they use A and B. So it's convenient if you simply forget this second form of the estimated equation. Let's move on to point number 2. Before fitting a regression line, the first thing that we do is to estimate whether there is a linear relationship actually existing between the two variables of interest. For that, we said we can draw the scatter plot and see if it shows a linear relationship. Or you can also calculate the coefficient of correlation, which is given by R. If your R is close to +1 or -1, then we go ahead and obtain the estimated linear regression equation. The estimated linear regression equation is given as y hat equals a plus bx. Now, what's the relationship between R and B? If your R is positive, your B should also be positive. If your R is negative, your B should also be negative. That's the simplest relationship. On the other hand, they are not going to be straight away equal to each other in value. The reason is R will exist only between -1 and +1. B, on the other hand, can take technically any value, any negative value and any positive value. Therefore, they will never be straight away equal to each other by numerical value. But remember, their signs are exactly the same. They both should be positive or they both should be negative. Of course, R is the coefficient of correlation. But this is the estimated coefficient of correlation. We simply need a sample and we can estimate the coefficient of correlation. And here, B is the estimated slope. The estimated values are also called statistics. Now, what are their parametric counterparts? Now, if this is the estimated coefficient of correlation, there should be a true coefficient of correlation as well. That's the reason we can estimate it. The true coefficient of correlation is called the parameter correlation. That's given by the Greek letter rho. This is read as rho. R-H-O. This is the coefficient of correlation parameter. So what's the parameter used for the slope? We already saw it. That is beta. Beta is parameter slope. Or you can say the true slope. And like I said earlier, both R and B must have the same sign. The same way, both rho and beta must have the same sign. Based on a data set, I can always calculate an equation for regression analysis. That's because if you enter a data set into your list L1, let's say our X data were entered into L1, and you enter your Y data into L2. And then you can simply run simple linear regression procedure and obtain an estimated equation between these two variables. Let's say my estimated equation is given by this equation. Y hat equals 0.0032x plus 55. Now, if I look at this equation, I can see my slope is really small. Well, in that case, will this slope really be required to be included in this equation? Can I just go ahead and write down y hat equals 55? Can I just go ahead and erase this first term? Because the slope is so small, 0.00032. When I obtain an equation, I cannot simply look at it and decide whether the slope is significant or not. The reason is, say, for example, x could be in millions. If x is in millions, million times this decimal place is still significantly larger compared to 55. To decide scientifically whether the slope should be included or removed from the equation, I have to do a proper hypothesis testing. So the first form of hypothesis is to simply see if my slope is significant. Or maybe I can see if the slope is significantly positive. I can also see if the slope is significantly negative. We look at that under point number 3. In point number 3, we try to answer the question whether I should include the slope in our regression equation or not. If I should include the slope in the regression equation, it should be significantly different from 0. If I should not include it in the equation, it should be simply equal to 0. So the slope parameter is given by beta. We know we use parameters when we write down the null and the alternative hypothesis. If I can simply go ahead and drop the slope, that should mean that the slope, beta, should be equal to 0. We write that under the null hypothesis. So the null hypothesis is beta equals 0. So the question could be, is the slope significant? If the question is just that, is the slope significant, then the alternative should be written this way. Beta is not equal to 0. Always, you must read the question carefully to figure out the form of the alternative hypothesis. Let's say the question is to see if the slope is significantly positive. It is not just significant. This time, the question is to see if the slope is significantly positive. If that's the case, the null hypothesis will still be written like that. Beta is equal to 0. But the alternative hypothesis should be written as beta is greater than 0. Now, if the question says, test if the slope is significantly negative, in that case, the null hypothesis will still stay same. Beta is equal to 0. The alternative hypothesis should be written as beta is lesser than 0. Now, based on this, we have a left-sided test here, we have a two-sided test there, and we have a right-sided test here. Do we have fixed critical values? No. The reason is, for regression, we only do a t-test. The full test ID is linear regression t-test. For t-test, we do not have fixed critical values. For t-test, the critical values always depend on the degrees of freedom, because t-distribution is not just a single distribution. It is a collection of distributions based on the degrees of freedom. To test these hypotheses, we have all three familiar methods. We have the confidence interval approach, we have the test statistic critical value approach, and also we have the p-value approach. However, these are just basic forms of null and alternative hypothesis. We can actually modify this one. Say, for example, I can ask the question, test if the true slope is significantly greater than 2. Or I can ask the question, test if the true slope is significantly lesser than 5. Or I can ask the question, test if the true slope is significantly different from 10. So that kind of situations can be written using a non-zero value on the right-hand side of these hypotheses. That's given under point number 4. This is for point number 3. Under point number 4, you can see that the true slope is compared against a given value. that given value is written as beta sub 0. So read the question carefully to figure out the value of beta sub 0. If you have to compare the true slope against, let's say, 3, then 3 is that beta sub 0. So in general, we will write down the null and the alternative hypothesis this way. I can write beta equals beta 0. And the alternative hypothesis will be either beta is not equal to that given value beta 0, or they can be like null hypothesis is beta equals beta 0 versus alternative is beta is larger than beta 0, or I can have null hypothesis of beta equals beta 0 versus alternative hypothesis of beta is lesser than beta 0. Simply read the question carefully and decide whether you have to compare against 0 or you have to compare against a specific given value. If you have to compare it against 0, we said we have all 3 methods. However, if you have to compare the true slope against a given value, statistics actually has all 3 methods. But there is a small limitation with your calculator. The calculator does not have a place to enter this beta 0 value when you run simple linear regression t-test. Therefore, practically, what we can do is only the confidence interval approach to test these non-zero right-hand sides only. Confidence interval method is used in this class. Construction of the confidence interval will be just the familiar way. If you have to do a 95% two-sided test, then we can straight away go ahead and construct a 95% two-sided T confidence interval for simple linear regression. And if you have to do a right-sided test, I will need a 95% upper confidence interval. How do you construct that? We construct a 90% two-sided, then replace upper limit with positive infinity. That should give you the 95% upper confidence interval for the true slope. If I need a 95% lower confidence interval for a left-sided alternative, I still go ahead and construct a 90% two-sided confidence interval. Then the lower limit is replaced with negative infinity to obtain the lower confidence interval. We don't have a limitation for upper or lower limits. We can simply use positive infinity for upper limit and negative infinity for lower limit, because the confidence intervals are constructed for beta, not for the coefficient of correlation. If the confidence intervals were constructed for coefficient of correlation, that should be restricted to -1 to +1, because correlation can only take the values between those two. But we don't construct confidence intervals for the coefficient of correlation. Confidence intervals are constructed for the true slope. The straightforward relationship between slope and correlation is that they both must have the same sign. They both must be positive or they both must be negative. Other than that, beta does not have a restriction. It can go from negative infinity to positive infinity, and it can take just technically any value between those two. Let's go to point number 5, distribution of beta hat. Do we need a distribution of beta hat? Of course, yes, we need. Why do we need a distribution for beta hat? Remember, when we did hypothesis tests on population mean, let's say mu equals 10 versus alternative, mu is not equal to 10 or something, we know we estimate mu using x bar. And the test statistic was developed using the distribution of x bar. The distribution of x bar is given by the central limit theorem, remember? So the same way, for hypothesis tests on beta, I will need the distribution of beta hat. Distribution of beta hat. This is very important. Let's say I have n pairs of data points for x and y. That means I have a data set like this. I have n number of pairs. So this is my first pair, this is my second pair, this is my third pair of data points, and so on. I have n number of pairs. That means I have n data points for x, and I have n data points for corresponding y values. The distribution of beta hat is a t distribution. That's why it is called simple linear regression t-test. So this is a t distribution. If I have n number of pairs, what could be the degrees of freedom? Now this one is extremely important. This is a place where many students make mistakes. Everywhere else outside of regression, t-distribution always had n minus 1 as the degrees of freedom. For simple linear regression, degrees of freedom will be n minus 2. Please remember that. The distribution of beta hat is a t-distribution with n minus 2 degrees of freedom. Please do not use n minus 2 as the degrees of freedom for anywhere else outside of simple linear regression. Now we can slowly derive a t-test. We have the confidence interval approach, we have the test statistic and critical value approach, and also we have the p-value approach. Now for the test statistic, here's the equation. The test statistic, t-test statistic for simple linear regression will be equal to beta hat over standard error of beta hat. This is actually given under point number 6. What is this standard error of beta hat? Now here's the standard error of beta hat. If you go to point number 7, you can see the calculated steps for simple linear regression t-test. That will give you the test statistic and also the degrees of freedom. Of course, you don't need the calculator to tell you the degrees of freedom because we already know that it should be n minus 2. However, if you have a fairly large data set, rather than counting one by one, it's easy to read the calculator's output for degrees of freedom. So once you know this t-test statistic, if you are testing a right-sided test, we can keep complete alpha on this distribution, right tail, and then see if the calculated test statistic is going to be on that rejection region. If you are testing a left-sided test, we keep complete alpha on the left tail and find the critical value using this distribution again, and then see if the test statistic is going to land on that rejection region. And if you are doing a two-sided test, we keep half of alpha on each tail of this distribution and then find two critical values. And those critical values are not fixed. And each time when you find the critical values, you will have to go to distributions and select inverse t. Degrees of freedom should be defined as n minus 2, and you can also enter area. In that function, area means always area to the left. Once you enter those things, you can get the critical value. That's the test statistic and critical value approach. We can also find the p-value once the test statistic is available to us. For right-sided test, you already know that the p-value is area to the right from the test statistic of this distribution. If you are testing a left-sided alternative, the p-value is area to the left from this point on this distribution. And if you are testing a two-sided alternative, half of the p-value will be from positive test statistic to positive infinity of this distribution. Or you can say half of the p-value is equal to the area from negative test statistic to the negative infinity of this distribution. And if you do half of p-value, for the full p-value, you will have to multiply that answer by 2. P-value test procedure is exactly same as always. If your p-value is lesser than alpha, you go ahead and reject your null hypothesis. And the remaining approach is the confidence interval approach. We can construct a confidence interval for the true slope beta. Here's the equation. Beta hat minus t critical value times standard error of beta hat is the lower limit, and beta hat plus t critical value times the standard error of beta hat is the upper limit. Of course, that equation is for two-sided t confidence interval for the true slope beta. And if you need a single-sided confidence interval, you already know how to obtain that single-sided confidence interval. When we discuss the applications, we will see how to construct those single-sided and two-sided confidence intervals. That's very fairly straightforward, just like previous examples. If you need a 95% two-sided confidence interval, you can straight away define 95% in your calculator as the confidence level. And if you needed a 95% single-sided confidence interval, using your calculator, you have to first construct a 90% two-sided confidence interval. And to obtain 95% upper or lower confidence intervals, you have to simply replace upper or lower limits with positive infinity or negative infinity, respectively. We will discuss the details of that when we discuss the example. And simply, to test the hypothesis, you have to see if that hypothesized value of beta is inside of that confidence interval. If it is found inside of the confidence interval, we accept the null hypothesis. If it is not found inside of the confidence interval, we reject the null hypothesis. The calculator steps for confidence interval construction are given in point number 9. You can stat, tests, and select G linear regression T interval. Before working on any hypothesis tests, just to make sure that we still remember the materials discussed in chapters 4 and 5, please go ahead and read problem number 10 and see if you can answer the 3 parts of that problem.
For the first part of this question, we need to obtain the coefficient of correlation R. Of course, we have to enter the given data set, but there is one small modification which we have to do for your calculator before calculating the coefficient of correlation R. What is that modification? You have to access catalog. You can do that by pressing second and number 0, and then you have to scroll down until you see diagnostic on. Scroll down and select diagnostic on. Note that there are 2 places with the term diagnostic. The first one is diagnostic off. The second one is diagnostic on. Select diagnostic on and hit enter. And then you have to hit enter again. On your screen, you should see diagnostic on done. After that, you can enter the given data set into 2 lists. We will enter X data points into the list L1 and Y data points into the list L2. And then we can run simple linear regression procedure. To enter the data set, we have to go to Stat, Edit, number 1, Edit, hit enter, and we will go ahead and enter X data points or the oil viscosity data points into the list L1. The first data point is 1.6, the second data point is 9.4, the third data point is 15.5, the next data point is 20, and the next data point is 22, 35.5, 43, 40.5, and 33. We will enter the where volume, the Y values, into the list L2. The first data point is 240, the next data point is 181, the next data point is 193, and 155, 172, 110, 113, 75, and 94. All right, so we entered the complete data set. Now, in order to calculate the coefficient of correlation, we have to go to Stat, select Calc, and then you can scroll down. There are 2 options. First place is number 4, linear regression AX plus B. That's what we used when we discussed chapters 4 and 5. But today, we will select the second option, which is given under number 8, linear regression A plus BX. Those 2 functions will eventually give you the same output, but there's a small catch. Under point number 4, the coefficient of X is written as A. Under point number 8, the coefficient of X is written as B. We are doing hypothesis testing. For hypothesis testing, the true slope is defined as beta. The estimated slope is defined as beta hat or lowercase b. Because of that reason, we will select number 8, linear regression A plus BX. Hit enter. X list. The default list is L1, and that's where we entered our data set. In case if you entered X data into a different list, you know how to define that. Let's say, for example, you entered X into list L5. How would you define that? Press second and number 5. we entered X data into the list L1 and Y data into the list L2. Therefore, there's no change needed for those two steps. And there's no frequency list. Skip that and skip the next line as well and select calculate and then hit enter. So here's the required output. The linear regression equation is given as y equals a plus bx, where a equals 234.07074 and b equals negative 3.5086. And in the next two lines, we have r squared and r. For this question, we do not need r squared. What we need is r. So the last line indicates the value of r. R equals negative 0.9378.
First part, the coefficient of correlation is equal to negative 0.9378. And you have to interpret this value. How do you interpret that? Interpretation of the coefficient of correlation was discussed in chapters 4 and 5 in detail. We said if the magnitude is between 0 and 0.3, that means overall if your coefficient of correlation is from negative 0.3 to positive 0.3, we say there is no linear relationship existing between the two random variables. If the magnitude of R is between 0.4 and 0.6, that means the coefficient of correlation is equal to 0.4 to 0.6 or from negative 0.6 to negative 0.4, we say there is a moderate linear relationship existing between the two random variables. If the magnitude of R is between 0.7 and 1, that means if your R is equal to something between 0.7 and 1 positive or from negative 1 to negative 0.7, we say there is a strong linear relationship existing between the two random variables. We must also indicate whether it is positive or negative. If it is positive, you can simply say increasing. If it is negative, you can simply say decreasing. Now this value is in the strong interval. So I have to say there is a strong. Now this is negative. Therefore, I would say decreasing. And always R gives you only the strength of the linear relationship. So I should include that term. Strong decreasing linear. Relationship existing between oil viscosity and wear volume. Second part, obtain the linear regression equation. The linear regression equation was found in the same calculator output that was equal to y hat equals 234.07 is the value of A. So A plus Bx. B is negative 3.509. So I will write this as a negative 3.509x. So that's the estimated regression equation between the two random variables, oil viscosity and wear volume. And then third point, what's the relationship between R and beta hat? We can see that R is negative, beta hat is also negative. R is equal to negative 0.9378. Beta hat, the estimated slope is equal to negative 3.509. So I will simply say they both have the same sign. Now, because they both have the same sign, if you are testing the basic form of null and alternative hypothesis for slope, which means in those cases the null hypothesis should be beta equals 0. The alternative will be compared against 0. If it is a left-sided test, you will write beta is lesser than 0. If it is right-sided, you will write beta is greater than 0. And if it is two-sided, you will write beta is not equal to 0. Now, in those cases, instead of writing beta, one may write using the coefficient of correlation as well, because they both have the same sign. When you compare against 0, let's say your alternative is beta is lesser than 0. What does that mean? I'm testing if the slope is significantly negative. Now, instead of doing this test, if somebody wants, they can write this as the parameter for correlation is equal to 0 versus the parameter for correlation is lesser than 0. Now, what's the symbol used for the parameter correlation? We used Greek rho. So you may write this also as rho equals 0 versus alternative rho is lesser than 0. However, please don't write this form for this class. We'll just keep the stuff simple. So we will simply use this one only. However, if you run regression t-test in your calculator, in the place where you select the alternative hypothesis, you would see both symbols, beta and rho. And your calculator only has the option to compare it against 0. So don't be confused when you see both symbols, beta and rho, because they both have the same way of writing. Let's go to point number 11. Use a data set given in point number 10 with x equals oil viscosity and y equals wear volume. We need to test if the linear regression is significantly negative. Part A, write down the null and the alternative hypothesis to be tested. I need to see if the simple linear regression is significantly negative. That means I need to see if the slope is significantly negative. So I will write down the null hypothesis as beta is equal to 0. The alternative hypothesis should be written as beta is lesser than 0. Always please read the question carefully. If the question was to see if the regression is significantly positive, you will have to write alternative as beta greater than 0. Null hypothesis is the same. If the question was test if the regression is significant, if it does not specify significantly negative or significantly positive, if it only says significant, then you have to go for a two-sided test where the null hypothesis is written the same way, the alternative is written as beta is not equal to 0. Part B, what's the appropriate statistical test procedure? Simple linear regression t-test. Or you can write linear regression t-test. Don't just write t-test. T-test is something else which was used for the comparison of population mean against a given value. We are not doing that here. We are testing for slope. Therefore, the complete test ID is linear regression t-test. Any explanation for why this test is conducted is not required because that's not asked in that question. But if it is asked, you will have to write because we are testing the strength of linear relationship between two random variables. For that, we have to go for linear regression t-test. Part C, construct a 95% confidence interval and test the hypothesis. Interpret the test result clearly. I need a 95% confidence interval, but I need a 95% lower confidence interval. So what's the first step? I must create a 90% two-sided t confidence interval for beta. For part C, I need 90% two-sided t confidence interval for beta. We will go to the calculator and first find that.
We have already entered the dataset into the lists L1 and L2. This is where we entered the dataset. So we can straight away go ahead and construct the required 90% two-sided t confidence interval for the slope. For that, you have to go to Stat, select Tests, and then you scroll down until you see linear regression t interval. It's given under G. Select G, linear regression t interval. Hit enter. X list is L1, Y list is L2, frequency is always equal to 1, confidence level. This time we need a 90% two-sided confidence interval. Therefore, the confidence level should be 0.90. Skip the next line, select calculate, hit enter. make sure that you hit enter only one time. The 90% two-sided t confidence interval for true slope is from -4.439 to -2.578. This output also has degrees of freedom, which is equal to 7. Why do you have 7 as degrees of freedom? Because in the data set, we had 9 pairs of data. For linear regression, the distribution is Tn-2. Since n equals 9, n-2 is equal to 7.
So the 90% two-sided t confidence interval for beta has a lower limit of -4.439 and the upper limit is -2.578. Now what I need is a 95% lower confidence interval because this is a left-sided alternative. Now I can obtain the 95% lower confidence interval. All I have to do is simply to replace this lower limit with -infinity. Upper limit stays same as it is, -2.578. Now, based on this confidence interval, I need to test this hypothesis. I have to see if 0 is found inside of this confidence interval. Well, the entire confidence interval is negative. That means 0 is not found inside of that. That means I must reject the null hypothesis. Rejecting the null hypothesis means our data eventually support this alternative. And we must interpret. So how do you interpret this? We always interpret H1 because our data supported this. This time we say we have statistical evidence with 95% probability to conclude that the regression between the oil viscosity and wear volume is significantly negative. We have statistical evidence with 95% probability to conclude that the true slope between oil viscosity and wear volume is significantly negative. Since I already used the term true slope, calling it significantly negative is not required. If you simply use the slope, you can say it is significantly negative. Since we used the term true slope, we can simply ignore significant. Or you can simply say we have statistical evidence with 95% probability to conclude that the regression is significantly negative between oil viscosity and wear volume. They both have the same meaning. You are not required to use the term true slope. You may use true slope or you can simply write the regression. Let's go to part D. Test the hypothesis using the critical value and test statistic method. Do you get the same answer? We have a left-sided test and our distribution is T7 distribution because we have 9 data points. For simple linear regression t-test, it is Tn-2 distribution. Therefore, we agreed that we are working with T7 distribution. Since this is a left-sided test, I must keep complete alpha on the left tail. Alpha is 0.05, and then I have to read this value from the inverse t distribution. Let's go to the calculator again.
To find the critical value from the T7 distribution, you have to go to distributions first, second, variables, that's where we have distributions, and then select number 4, inverse t, hit enter. Area is always area to the left, which is alpha, which is equal to 0.05. Degrees of freedom is equal to 7. Select, paste, hit enter, and hit enter again. Critical value is negative 1.895.
We saw the critical value is negative 1.895. Now we need to calculate the test statistic. Let's go to the calculator again.
We have already entered the given data set, therefore there is no data entry step. We entered X data into list L1 and Y data into list L2. Now we can straight away calculate the linear regression t-test statistic. For that, you have to go to Stat, select Tests, and then you scroll down until you see linear regression t-test. It is given under letter F. Select letter F, linear regression t-test. Hit Enter. X list is L1, Y list is L2, frequency is always equal to 1. In the next line, you have to define the alternative hypothesis. Our alternative hypothesis is beta is lesser than 0. As I indicated earlier, when you compare it against 0, you can write beta or you can write rho. But for this class, we will simply use beta. Our alternative hypothesis is beta is lesser than 0. Select lesser than 0 and hit Enter. Skip the next line, select Calculate, and then hit Enter. The second line of this output indicates your alternative hypothesis. The alternative hypothesis is beta is lesser than 0, which is also equivalent to rho is lesser than 0, where rho is the coefficient of correlation. We do not focus on that part. Simply look at the first part of the second line. Beta is lesser than 0 is the correct alternative hypothesis we need to test for this question. Therefore, we can simply go ahead and use the rest of the output. The t-test statistic is given on the third line, which is equal to negative 7.144. The fourth line indicates the p-value. Remember, when you read the p-value, pay attention to the final part, e-5. That stands for 10 raised to the negative 5, which means the p-value for this test is 9.314 times 10 to the negative 5.
We saw the t-test statistic is equal to negative 7.144. Clearly, this test statistic is in the rejection region. Therefore, we reject the null hypothesis. That means we get the same interpretation as earlier. That means we have 95% probability to conclude that the regression between wear volume and oil viscosity is significantly negative. Or you can say the slope between those two variables is significantly negative. And we do not have to write that interpretation again because we already wrote it down in the previous part. Part E, what's the p-value of the test? Test the hypothesis using the p-value. Do you get the same answer? The p-value was found in the same output, 9.314 e-5. So what does this mean? That means your p-value is equal to 9.314 times 10 raised to the negative 5. Please make sure that you write down this part of the p-value. Clearly, that p-value is lesser than alpha, which is 0.05. So whenever the p-value is lesser than alpha, we reject the null hypothesis. So once again, we get the same conclusion. Therefore, we do not have to write the interpretation again. Let's go to point number 12. Use the data given in problem 10 with x equals oil viscosity and y equals wear volume. Write the appropriate null and alternative hypothesis. Use appropriate confidence intervals and test the following hypothesis. Under part A, we have test if the slope is significantly lesser than negative 3. How do you write the null and the alternative hypothesis? I should write the null hypothesis as beta equals negative 3. The alternative should be written as beta is lesser than negative 3. Now I need a 95% lower confidence interval for beta. We already constructed a 90% two-sided T confidence interval for beta, which was, we write it here, 90% two-sided confidence interval for beta was equal to negative 4.439 was the lower limit, negative 2.578 was the upper limit. Using this 90% two-sided confidence interval, I can of course obtain a 95% lower confidence interval, which is what I need for testing this hypothesis. The 95% lower T confidence interval for beta is equal to, I simply have to replace this lower limit with negative infinity. Upper limit stays same as negative 2.578. Now I have to see if negative 3 is found inside of this confidence interval. Is it inside of this interval? Yes, right? Negative numbers are slightly confusing. Remember, between negative infinity and negative 2.5 something, negative 3 is found inside. So I will say negative 3 is inside of the confidence interval. Therefore, we accept this null hypothesis. Or you can say we fail to reject the null hypothesis. Because usually, always our objective in hypothesis testing is to see if we can somehow reject the null hypothesis. When we cannot do that, rather than calling it accept the null hypothesis, we prefer to call it we fail to reject the null hypothesis. So we accepted the null hypothesis means our data do not support this statement. And we must interpret that. Because of this reason, we say we have no statistical evidence. With 95% probability to conclude that the true slope between oil viscosity and wear volume is lesser than negative 3. We said we have no statistical evidence because our data did not support the alternative. And of course, we have write down the complete alternative inverse. True slope between oil viscosity and wear volume is lesser than negative 3, which is this alternative hypothesis. Let's go to part B. Test if the slope is significantly lesser than negative 1. I need to write down an alternative hypothesis. We write null hypothesis as beta is equal to negative 1 versus the alternative hypothesis as beta is lesser than negative 1. Here's the previously constructed 90% two-sided confidence interval for beta, going from negative 4.439 to negative 2.578. 95% lower T confidence interval for beta was negative infinity to negative 2.578. So is negative 1 found inside of this confidence interval? No. Negative 1 is larger than negative 2 point something, right? Therefore, negative 1 is not found inside the confidence interval. Negative 1 is not found inside the confidence interval means we have to reject the null hypothesis. So rejecting the null hypothesis means our data support this alternative. And we must interpret that statement. Our data supported this. Therefore, we say we have statistical evidence with 95% probability to conclude that the slope between oil viscosity and wear volume is significantly lesser than negative 1. We will write it as we have statistical evidence with 95% probability to conclude that the true slope between oil viscosity and wear volume is lesser than -1. Let's go to part C. Test if the slope is significantly greater than -1. In that case, I have to write down the null hypothesis as beta equals -1 versus the alternative hypothesis beta is greater than -1. Once again, I will need a single-sided 95% confidence interval, for which I have to start with 90% two-sided confidence interval that we previously constructed, which we saw as -4.439 to -2.578. This time I need a 95% upper confidence interval. The 95% upper confidence interval for beta is, we have the same lower limit, -4.439. The upper limit is replaced with positive infinity. Now I need to see if -1 is found inside of this confidence interval. Clearly, -1 is inside of this confidence interval. That means I have to accept null hypothesis. Null hypothesis is accepted means our data do not support the alternative. We write this statement as the interpretation. Because of that, we say we have no statistical evidence to conclude with 95% probability that the slope between the oil viscosity and wear volume is significantly greater than -1. We have no statistical evidence with 95% probability to conclude that the true slope between oil viscosity and wear volume is greater than -1. One small comment. Since I used the term true slope rather than just slope, you are not required to write significantly greater than -1. If you didn't use the term true, if you simply use the term slope, then it's recommended that you write it as significantly greater than -1. That ends chapter 26, Inference for Regression. Thank you.